Welcome everyone. In this video lecture, we will think about the very fundamental analog building block that is our differential amplifier. So basically differential amplifier is considered as a fundamental building block in analog integrated circuit design. In analog IC design, the differential amplifier plays a very important role, and one of the simplest example of the differential amplifier is a input stage of a op-amp is a simple differential amplifier. The input stage of every op-amp is considered as a differential amplifier, and the BJT is a differential amplifier. BJT can be used as a differential amplifier and may be a preferred choice for a very high speed emitter coupled logic family that we know. So BJT based differential amplifier is preferred for the design of very high speed emitter coupled logic family. So the very fundamental design with the passive load of a differential amplifier is like this. Means this one is the BJT based. Okay, this one is the BJT based circuitry of a differential amplifier where two BJT is there, Q1, Q2, okay, and RC the resistance across the collector side, and we are taking output from the collector VC1, okay. So let me write. Means this one is the supply voltage, okay. This one is our supply voltage, clear, and this one is one transistor, and this one is our what, VC1. Why? Because this one is a collector of transistor 1, base of 1, okay, and emitter 1, and this one is our emitter 2 point, and this one is collector 2 point, simply right, and this one is B2. So we are giving some voltages across the base of transistor 1, base of transistor 2, and these two are connected together, both the emitter are connected together, and it passes through a current source and some negative supply is there. So this one is the fundamental basic differential amplifier circuit, okay. Next, and the MOS one is also very simple. The the MOS differential amplifier, as we know, there is a gate terminal, this one of gate of 1, and this one arrow point always the source one, the source terminal, and drain terminal, we are taking the output from the drain one, that is our VD1, and this terminal is our drain of 2, we are taking output VD2, and this one is our gate 2 where we are giving input VG2, and the source S1 and S2 are grounded, sorry, connected to some current source I, that is our this, and minus VSS. So we will discuss in detail today about the MOS based differential amplifier. So this one is the fundamental active building block for the differential amplifier using two MOS MOS pair. Okay, so this one is some design that we have to consider for the analysis purpose. So now the first point is our why differential amplifier is suited for integrated circuit fabrication. Very important question is there, and I have taken this idea or the concept we have collected from the microelectronic circuits book. Why differential amplifier is suited for the integrated circuit fabrication. So the very first point is the performance of a differential pair depends critically on the matching between the two pairs of the circuit or two sides of the circuit. Okay, basically in differential amplifier there are two pairs which is somehow matched. Okay, for this purpose I just want to show you some figure. Why differential is suited for the integrated circuit fabrication? Means see, here there are two transistors Q1, Q2, both having the mesh property. Okay, both having this similar kind of parameter, or they are very symmetrical kind of structure. So both having matched one. So the performance of a differential pair depends critically on the matching between the two sides of the circuit. Okay, so in any IC design we require the performance where we have to go for a very similar or very symmetric kind of circuitry. So the performance of differential pairs depends critically on the matching between the two sides of the circuits. Okay, so that's why this circuit differential amplifier is somehow symmetrical. We can see if we draw a line. Okay, if we draw a line in between, okay, see both are symmetrical, mirror image. So in IC design, in IC design, okay, the performance of the differential pair depends critically on the matching between the two sides of the circuits. Okay. The other point, integrated circuit fabrication is capable of providing mesh devices whose parameter can be tracked over wide ranges of changes in the environmental condition. So basically in IC fabrication is capable of providing mesh devices whose parameter can be tracked over the wide ranges of changes in environmental conditions. Okay. Next point, a differential amplifier uses more component than single inlet circuit. So that's why we have to go for the integrated circuit technology, because IC technology enables the availability of large number of transistors at relatively low cost. So that's why differential amplifier uses more components. So we have to go for the IC design technology or integrated circuit technology, which requires or which enables the availability of large number of transistors at relatively low cost. Okay, I will try to share these notes, PDF notes, in our link also. Okay, now, differential circuits are ideally suited for IC fabrication where large capacitors are impossible to design or fabricate economically. Okay, so differential circuits are ideally suited for IC fabrication where large capacitors are impossible to fabricate. Okay, now next. Now, the first question was why differential amplifier is suited for the integrated circuit fabrication. So that part, the same thing is written here. Okay, so that part we have cleared. Now we have to go for the next point. Okay, this one is also same. Why differential amplifier is a better choice in comparison to single inlet amplifier? So the answer is differential circuits are much less sensitive to noise interference than single inlet circuits. Actually, in differential amplifier, what we observe that it is very less sensitive to noise and interference than single inlet circuits. Okay, see this one is a op amp and we are giving some signal. Okay, invert signal to the inverting in, say I am saying Vi signal and V plus signal from the non-inverting, and some noise is there. But after the output, this noise will be cancelled out. Okay, due to the property of V plus minus V minus. So the overall noise will be cancelled out. Okay, so that's why differential circuit are much less sensitive towards the noise. Okay, in comparison to the single inlet circuitry. Now differential amplifiers enables us to bias the amplifier and to couple the amplifier stages together without the need of any bypass capacitor and coupling capacitor, which is the not possible in case of the single inlet circuit. In differential amplifier we have saw that there is no coupling capacitor, bypass capacitor. Okay, so this one is the two important point through which we can say differential amplifier is much better in comparison to the single inlet amplifier because it is very less sensitive to the noise. There is no use of bypass capacitor and coupling capacitor. Okay, the most differential amplifier. Now the most differential amplifier. So today now we will discuss in detail the most differential amplifier. So as we discussed in the very beginning that the most differential amplifier uses two transistors, that is our Q1 and Q2, where through this gate in, okay, through this gate in, say G1 and G2, we are just giving the input VG1, VG2, and through the drain D1, we are taking the output, and this one is our source terminal, source 1, source 2, and this one is our drain 2, okay, and the current in the circuit is id1 id2, okay, the same current will go id1 id2 because this is very of a very high input impedance, so there will be negligible current, and the current I and minus vss supply. So two mesh transistor are there, q1 and q2, two mesh transistor is there, q1 and q2, okay. Then source of q1 and q2 are joined together. Source of q1, source terminal, arrow sign always shows the source terminal of the MOSFET. So source of q1 and q2 are connected or joined together by a constant current source I, okay, through a constant current source I. Here the current source we have taken is ideal and has infinite output resistance. Okay, this current source having infinite output resistance. R naught we have taken infinity for a perfect current source. Okay, R naught we have taken infinity for a infinity output resistance. Okay, now two resistors load as a RD for Q1 and Q2. Okay, two load RD as a for the Q1 and Q2, and we are taking output from the drain terminal that we have considered. Now each drain terminal is connected to a positive power supply through a VDD, through a resistor RD, okay, that we have already saw. And load may be active load. The load we are taking here is a passive resistance RD, but we can take the active load. We will discuss it later. Means instead of the RD resistance, we have to take some more space current mirror circuitry as a load that we will discuss later. So now we will start the MOS differential pair with a common mode input voltage. Okay, MOS differential pair with common mode input voltage. So what we are doing, this gate 1 and gate 2 are connected together through a common voltage, say VCM. Our topic is MOS differential pair operation with a common mode input voltage. Common mode input voltage, that is our VCM. Okay. So VCM is the common mode input voltage, the gate one. So this voltage is plus minus VGS, and this drain D1. Okay. And drain D2. The point this one, the drain terminal of this, and I. So we have written the current I2 in this side. Okay. This one is our the current I. So this I is nothing but simply both the transistors meshed. So this should be I by 2, I by 2. And so this current will be also I by 2, I by 2. Okay. So the corresponding voltage across this point will be VDD minus I by 2 RD. So that we have written here. Is it okay? VD2 is nothing but simply VDD. VD2 means this voltage VDD minus I by 2 RD. Okay, clear this one? So here the two gate terminals joined together. Okay, the gate terminals G1 and G2 are joined together and connected to a voltage source, that is our common voltage, that is our VCM is termed as common mode voltage. Okay, next, so VG1, the voltage across the VG1 and VG2 is nothing but simply our VCM. Okay, already written here. Okay. Now since Q1 and Q2 are matched, hence the current I will be divided equally, and it will be I by 2 through the source of S1 and I by 2 through the source of S2. This one is our S1, S2, source of second transistor, S2. So we can write the current will be ID1 and ID2 will be I by 2, because the current IG1 and IG2 will be nearly 0. So we are not bothered about this one. So ID1, ID2 will be also I by 2. Now the voltage at the source of The voltage, the source of Q1 and Q2 is Vs is Vcm minus Vgs. That point we have to. The voltage, so this voltage, I am saying this voltage, okay. If anyone have to write this voltage Vs, so this Vs can be directly written as this voltage Vcm minus Vgs. This voltage is nothing but simply this minus this. Okay, simple. So this voltage across the source, or this point, say I am saying say all are S. So Vs is Vcm minus Vgs. Okay, that point we have written here. Get to source voltage. The source voltage of Q1 Q2 is Vs is Vcm common mode voltage minus the get to source voltage corresponding to drain current I by 2. Now, a relationship between VGS and I by 2 can be developed by neglecting channel length modulation. Hence, we have to write the drain current equation in the saturation region like ID equals to 1 by 2 Kn dash W by L VGS minus VT whole square. So, this should be ID is nothing but simply I by 2 and 1 by 2 Kn dash W by L VGS minus VT whole square. Okay. So, if we solve, this 2 and 2 will be cancel out. So I equals to K and dash W by L VOVY. So this VOV overdrive voltage is nothing but simply VGS minus VT. Okay. So VOV will be simply a square root of I by K and dash W by L. Okay. So overdrive voltage, and the voltage at each drain will be simply VDD minus I by 2 RD, because this one is our VD voltage. Okay, and this one is the resistance, and we are taking here the current, the voltage VD1, and this one is RD, and some current is going like I by 2. So VD1 can be written as this voltage VDD minus I by 2 into RD. So this we have already written here. So now the the difference between the voltage between the two drains will be always zero. If we do VD1 minus VD2 will be always 0. Okay, thus the difference in voltage between the two drains will be 0. When we vary the value of the common mode voltage VCM, the current I will also divide equally. If we change the value of VCM, okay, the current I will be equally divide between Q1 and Q2. At the drain will not changes, and the voltage at the drain will never change. Okay, thus the differential pair does not respond or rejects common mode input signals. Thus the differential pair does not respond to common mode input signal. Okay, clear? Now, input common mode range is an important specification of a differential amplifier. So, input common mode range is an important specification of a differential amplifier. And when both the transistor is in saturation, Q1 and Q2 is in saturation, so then the highest value of VCM, the common mode voltage, will be VT plus VDD minus I by 2 RD. So this one is basically our what? VD. So maximum VC max will be VD, okay, plus VT. VD plus VD. Okay. And the lowest will be VCM is determined by the need to allow for a sufficient voltage across current source I for it to operate properly. Okay. So VCM minimum will be minus VSS plus VCS, the voltage across the current source. This one is the voltage across the current source, voltage across the current source, okay, and VT plus overdrive voltage, okay. Now the summary. Now we have made a summary for this MOS differential pair with common mode input, okay. So this one is the circuitry. Say this one is our gate 1, drain, drain 2, gate 2, and source, okay. Say S1, S2. So VOV, the overdrive voltage. This one is our overdrive voltage. So the overdrive voltage VGS minus VT, and VD2 simply VDD minus I by 2 RD. Okay, that the same thing VD1, VGS, VT plus VOB. If both are in saturation, we can find VGS equals to VT plus I by this. Okay, this can be easily derived by I by 2, saturation current I by 2, 1 by 2, then VOB is like this. And the source voltage Vs, this Vs will be simply VCM minus VGS. Simple Kirchhoff's voltage law. And input common mode range will be like this. Vc max Vt plus Vdd minus I by 2 Rd, and Vcm minimum will be minus Vss plus Vcs plus Vt plus Vob. And for difference, you can go for the microcontroller circuits book. For more detail, I have made these notes from the microcontroller circuit book. So this is all about the simple fundamentals of the differential MOS pair operation for the single common mode input, and why differential amplifier preferred choice for the over the single ended inputs I have covered. Okay, and why it is useful in IC fabrication also we have covered. So this is all about this video lecture. So thank you for watching this video. Thank you.